however we call. And so, okay, Professor Boris Chichkov, coming from Leibniz University, Hannover, Germany. I will make prompt and personal let's say, introduction. In 2005, I was learning the things in Leserzentrum Hannover, in professors led department of nanotechnology at that time, together with, at that time, still PhD students, Karsten Reinhardt, Alexandrov Sanikov. And so, okay, you already know what I'm doing and from where I learned it, so it's nothing new. But one thing, one detail I will tell. So what I learned more than that from Boris, it's to wear trousers with pockets on sides, as you might see, which are very, very convenient. So I'm pretty sure today Boris will tell also us many things which we can learn, use, and we are very happy to have him here. And he will make a great presentation. So, please.
Okay, thank you very much. So you can hear me, yes? So this is how Leibniz University looks like. And today I will speak about laser printing. Laser printing of nanoparticles, so direct printing of nanoparticles, laser printing of living cells and microorganisms, and of course a little bit about scaffolds, what we do with them using two-photon polymerization. Good. There are many things which you can do with lasers, and even many, many really new things. And but before we will start to speak about laser printing, I would like to discuss with you some philosophical, probably, topics. The origin of photon mass, momentum, and energy in the electric medium. So we will speak about a photon. So this was a recent publication. Okay. And so the nature of light, what is a photon? Of course, since we are working with lasers, you should know the answer, what is a photon. So in the beginning of the last century, in the previous century, Max Planck introduced the concept of quanta of energy to explain blackbody radiation, probably you remember. In 1905, Albert Einstein introduced the concept of light quanta to explain photo effect. But when he was already old, and after 50 years, he has written all the 50 years of conscious brooding, it means strong thinking, have brought me no closer to answer the question, what are light quanta? Of course, today every rascal means every student thinks he knows the answer, but he is deluding himself. He is really not thinking properly. But I would like to show you a few examples from this, and also, if you would like to read about what is photon, this is a recommendation in Optics and Photonics New. This is a nice collection of papers. So usually definition of photon. Photon, also called light quantum, is a teeny energy package of electromagnetic radiation. Yeah? So usually we get a photon when atom is excited and then radiates, so we produce a photon. And also what we want to know in my discussion today, what is a quasi-particle? Sorry, I press always the wrong button. Quasi-particle in physics is a disturbance in a medium that behaves as a particle and that may conveniently regarded as one. Good, you know that we deal with the wave-particle duality, so that the photon and also the elementary electron, they have both wave and particle nature. And we know this due to both Planck and Einstein. But what you probably not really well know, and I have already noticed this, for example, Ewald-Ozin extinction theorem. If somebody knows this, is somebody heard about this theorem? No. So this is, when you look at the principles of optics, then you will see and read that you know it's good, that velocity of light decreases in the dielectric, it is equal to speed of light divided by the refractive index. When light traveling in vacuum enters a transparent medium like glass, the light slows down, and as described by index of refraction. And this fact is well known, but it's actually quite strange and surprising from the microscopic point of view, how it happens that the light is somehow braked when it goes into the dielectric. The light in glass is a superposition of the original light wave and the light waves, dipole radiation emitted by the atom. By the atom, it means bounded electrons, in the oscillating electrons in the glass. And what the Ewald-Olsen extinction theorem says, that the light emitted by the atoms has a component traveling at the speed of light in vacuum, which exactly cancel out, extinguishes the original light wave. So it means that the atom in the glass radiate the same wave, but okay, with a different phase, and it is cancelled. Additionally, the light emitted by the atom has a component traveling at the slow speed of light in glass. Altogether, the only wave in the glass is the slow wave. Okay, this is theorem. It has a proof, of course, but we will not speak about this. We will go to, to momentum, mass and energy of light. Probably you have already heard that there were two guys, Max Abraham and Hermann Minkowski, and they have introduced momentum of light. And for example, Abraham said that the velocity of light decreases in the dielectric, and therefore momentum must also decrease. He has written this expression for the momentum, which follows directly from this energy relation in special relativity between momentum and energy. This is the velocity. If you put here light velocity, c divided by n, and energy of the photon, then you will get this relation immediately. Minkowski said, wavelengths of light decreases in the dielectric and the momentum must increase. Light gains momentum. You know this formula. And still there are many papers devoted to this controversy, discussing what is wrong. And of course, I have to also to discuss it. Okay, in the dielectric, wavelengths is, okay, the frequency is the same, is not changed, but light wavelength changes, and speed of light also. So this is equivalent. From the wavelength changes, the speed of light also changes. So this is equivalent statement. Again, this is a Minkowski momentum, which emphasizes, usually people write in the literature, emphasizes the wave nature of photon, and this is the Abraham momentum, which emphasizes the particle nature of photon. And between this momenta, the following relation exists. Minkowski momentum is n squared larger than the Abraham momentum. What we know, you also, we all know that the Minkowski momentum is correct. So this is the momentum of light. Arguments in favor of this Minkowski momentum follow from the Snell's law. You can get Snell's law directly from this. Nonlinear optics, we use for phase matching also this expression for the momentum, laser physics, Doppler and Cherenkov effects. But how we can prove it? How we can prove that this momentum is right? For example, if you start thinking simply, so you know that, for example, that, that the photon, that the photon has energy and mass is equal to 0, and the special relativity, you have this connection between the energy and the momentum. If you put here momentum for Abraham, or you can put here momentum from Minkowski, then you will see that in both cases, if you assume that mass is equal to 0, you will get such inequalities. So you should somehow deal with this. So it means that photon, when it enters into the medium, it has mass. So outside in the vacuum, in the air, his mass of the photon is 0. But in the medium, it has mass. And this follows from this relation. So this is a relation, interesting relation from between the energy and the velocity, from the special relativity. If something has energy and something moves with velocity which is slower than the velocity of light, it has mass. So you see here, mass should not be equal 0. It means the photon, when it comes into the medium, is getting mass. Good. There are some simple relation between the energy and mass. So this is a special relativity. This is a Pythagorean relationship, Pythagorean theorem. And it is, okay, representations, which is quite simple, which allows you to understand using triangle and Pythagorean relationship, what happens when, for example, the mass grows, or what happens when the momentum grows. So you see immediately these relations. And for example, when you have particle at rest, mass is larger than 0. So this, you have this line. And when you have mass is equal to 0, you have this line. But to have mass equal to 0, you need to have velocity which is equal to the velocity of light. Good. Now, photons in dielectric media is relativistic quasi-particles. So we call it M photons, just to emphasize that this photons has mass. Now, how we can define this mass? For example, we have this expression for the momentum here, relativistic momentum. We can write it equal to the Abraham's momentum or Minkowski momentum, and this is the speed of light. When we do this, this is the mass of photon due to the Abraham, this is the mass of photon due to Minkowski, and this is the relation between these masses. So photon has mass, and this is the relation between them. Energy. When we look at the energy, okay, you have for the Abraham photon, energy is equal to the photon energy, but for the Minkowski, energy is equal n squared multiplied by the energy of the photon. I told you that we use the Minkowski relation for the momentum, but this Minkowski relation tells you that the energy of the photon is equal to the n squared times frequency, energy of the photon. So these both expressions, they fulfill the four momentum of photon. It satisfies Lorentz transformation. Everything is fine with this. But again, what we have here, so I would like to prove you that the Minkowski expression is correct here. But you see here the mass of the photon, not only momentum grows when the photon comes to the medium, but also energy of the photon grows by n squared. You have never heard about this. Definitely, nobody of you. But this is known fact. This is known fact. And to fulfill the energy conservation, you should write, this is energy of the photon, this is the energy of the photon at the medium, and this is the potential energy. And this should be negative, and negative potential energy of the photon inside the medium. So there are textbooks where you can find it. When the photon goes into the medium, its potential energy is negative. It is not helping you much, probably. Yes, why? Why the potential energy of the photon became negative in the medium? Okay, so we will give an answer to this. Look, so we will assume that when the photon comes into the medium, then its energy will be transferred to kinetic energy of the quasi-particle. Photon generates quasi-particle, and quasi-particles moves in the medium with the velocity of light, c divided by n, and we can calculate mass from here. So when we calculate mass from this equation, we will see that this mass has two components, Minkowski mass plus something else. And this something else, this is the mass, is the effective rest mass of dipole oscillations of bound electrons induced by the photon. And as I said, this is the Minkowski mass which corresponds to the momentum which we usually use. And the rest mass of the M photon is determined in the moving frame. So the rest mass of M photon, Minkowski photon, is determined in the moving frame, and of the oscillating dipoles in the laboratory frame. And there is this connection between these masses. You see here, as it should be in relativistic theory. So, and the energy conservation for the photon becomes, so this is the Minkowski part corresponding to the Minkowski momentum, which we usually use. And this is the rest energy of the dipole oscillations of bound electrons induced by the photon. Good, so this potential has a simple meaning. This is just the rest energy. Okay, if you also introduce, for example, this refractive index here inside, and then you can show that this rest mass is equal to this. So this you recognize that this is a first order linear susceptibility, and this is the expression for the mass, for the rest mass of the dipoles, which are excited by the photon. Good, of course, this is a diagram which shows these processes, how light is scattered in the medium. Okay, and this is a summary of this. So when photon enters in the medium, so its energy is equal by this, its momentum is equal by this, and everything is in agreement with the energy conservation, with the special relativity, everything is fine. But what is more complicated? When we come now to the dispersive medium, where refractive index depends on the frequency. You know that in this case, we need to use group refractive index. This group refractive index is determined by this. So this is relation between ordinary index and this is a group. And we know that the light moves with the group velocity, so we now need to use this expression with the group velocity. And what we get from here that the Minkowski momentum in such a medium should be given by this formula where we have group refractive index instead of normal refractive index. When you look in the literature, that you will find also two papers, Miloni, Boyd. You will find this expression for the momentum of light in a dispersive medium. You see here, refractive index squared divided by the group refractive index. Barnett and Loudon, they have this one. Good, but only this one is consistent with the special relativity in the velocity of light, which is given by the formula which I showed you above. Okay, so just a few examples. For example, when you use this refractive index and when you go to the high frequencies, at high frequencies n is smaller than 1 refractive index, when you go to the X-ray, for example, area, then the phase velocity will be larger than c, only the group velocity is smaller, and when we use the formulas which I have derived with this refractive index for the group velocity, then you will get momentum, which is shown here. And in a medium with negative refraction index where n is less than 0, the light momentum defined by this formula is oppositely directed to the group velocity, so we have negative light pressure. But this scenario is difficult to combine with the behavior of a single photon quasi-particle and the formula which I have derived on the basis of special relativity. They correspond to the positive pressure, and also modeling which has been done by different people. They show that even in the medium with negative refractive index, you have a positive light pressure. Good. So the challenge for young people, how to measure the momentum of light in the medium. How to define it, what formula is correct. So we have 3 formulas which are shown to you. So wonderful material is polydimethylsiloxane, PDMS, which is a stretchable material. So it has Young modulus, and you can easily calculate. So when light comes in such a medium, this medium will be stretched due to the light pressure, stretched. And so the changes in the medium, so estimates are given here. So these estimates can be measured, for example, using interferometric measurements, so you can measure these changes, and then you can distinguish which momentum is correct. So I address you to my paper concerning this, and probably you will be able to measure this. But the effect is already used. So people are using this effect. So some people are making optical stretching of cells. So they just, can use light, as you can see here. And in the light, these cells are stretched, and they can measure elastic modulus of the cells without even thinking momentum of photon, etc., and other properties. Okay, I stop here now, and I will come back to the laser printing. The only message which I wanted to give you that, again, guys, even photon in the medium is something more complex than you are thinking about. And therefore, probably, it is interesting also for you to read something about this and to think. So, femtosecond laser ablation and microstructuring. I have started to work on this topic in 1995. In this paper we have written, it became very famous. This is one of my famous papers with more than 3,600 citations. And by chance, this paper was the best paper ever published in Applied Physics A during 50 years history. And that is why they have invited me to write something in this 50th anniversary of Applied Physics. And I have written here a paper about laser printing trends and perspectives. So everything in a very compressed form, what I'm telling you today, you can read in this paper. So many, many things. Therefore, I address you to this paper. And now we will start discussions. So laser printing of nano and microparticles. So what we are doing for a long time. So when you, for example, usually I explain it like this. When you throw a stone in the water, you will see this development. You will see a jet, and you will see a droplet, and the droplet will be detached from the jet. And exactly the same happens when we focus laser light on the metal film, for example, on the glass. We produce a small jet, and the particle is detached, is flying, and we can print them. So we have shown that this works very well. We can print nanoparticles, and I will tell you about this, what can be done with this. So it works both in the forward and backward direction. So the particles are flying. So you can produce very beautiful, you see here a lot of papers which we published. You can make lenses, you can study how surface plasmon interact with these particles, you can do a lot of fine stuff, you can make really very small nanoparticles arrays. This shows you the size of the particles, how it is determined by the thickness of layer and the focusing condition of light. But when you make lithographic pre-patterning, then you can, by a single laser pulse, femtosecond of course, you can generate millions of particles which have all the same size, which is determined by, again, the mass which you have in these islands. So this is a beautiful pictures which we have printed. You see here with nanoparticles by single laser pulse. And we have used this as a sensors. And you can do any metal you can print. Here we, for example, printed iron. This is magnetic particles. But of course, this is what concerns to metal. But we can print also dielectric particles, semiconductor particles. And this is something what we have started to do many years ago. When we ablated silicon targets, then we have observed that there are debris, nanoparticle debris on the surface. And in the dark field microscope, where we don't have light, we have only reflected light, we see such pictures, beautiful colors. So I had a theoretician at this time, Andrei Vlyukhin, and I have said to him, you should explain me this, why? And the fact is that the scattering, misscattering of this particle depends strongly on the size of this particle. You see here, and moreover, such particles, they are characterized by magnetic dipole resonance and electric dipole resonance, and they are, as I said, sensitive to the size of these particles. We have measured this for the first time in the world. This was nanolattice 12. We have demonstrated that, really, these two resonances, magnetic dipole and electric dipole, exist. So magnetic dipole, this is simple oscillation of the electron, electric dipole, sorry, and the magnetic dipole is displacement current oscillation on the surface. Okay, and now this is a big topic. Probably you know that many people are involved in investigation with dielectric nanoparticles, creating metasurfaces, etc. So we can print this also. And again, if you are interested, this is very simple stuff. So you can print nanoparticles from silicon. So we've shown this, that when we print them from crystalline, thin crystalline film, we produce them in amorphous phase, but we can, re-radiate it with another laser pulse. And this experiment, which was done with the same particles, so amorphous phase, then intermediate polycrystalline phase, this is a crystalline phase, and you can do it. Even if you just, control the distance between this donor slide and sample, then you can also influence the phase. We can print also in the forward direction of these particles. And unsolved topic, unresolved topic, which is again can be interesting for you since not all laser technologies are developed. This is additive manufacturing with, for example, with particles. So this is a preliminary work which we have done. So we printed particles on top of each other. Okay, so it works, it is simple. Good, now we printed much more particles on top of each other. So this is a spectral ratio of 40 silicon particles on top of each other. This is iron particles here. So you can print them. So you show here beautiful papers. This is our review in nanophotonics. So you can really print particles on top of each other, making idols. Why it is important? It means when you use different nanoparticles, you can create new materials. You can create materials which have all kinds of properties which you want. Since you have here semiconductor nanoparticle, metallic nanoparticle, dielectric nanoparticle in the mixture, and you can do it. And this is a new field. Not much is done in this field, and it can be done. What you can do else? You can generate colloidal nanoparticle by laser printing, which we have not also demonstrated, but this is important. So we have demonstrated in a small amount, but it is important since when you have 100 kilohertz repetition lasers, or megahertz repetition lasers, you can generate million particles per second. And what is good here, since when you generate them by this method, they all have the same size. They are mono. So this is a mono, colloid, yes, colloid, where the particles are the same. And also in this case, you can generate, for example, particles of the micrometer scale, which is difficult to make chemically. So it means this is a new approach for the generation of particles, which is not developed. And why I'm saying about this, since we personally, we cannot develop everything. So we have many, many things which are simple, but we cannot go in this direction. Additive manufacturing, you know that additive manufacturing plays now a very important role. So by laser printing is, again, unrealized project idea. Usually we use powder, commercial powder, and powders, also harmful, dangerous products, and usually this is the particles in the size 20, 100 micrometers. But you can make additive manufacturing by laser printing. So some people started to do it after my talks. For example, these guys do a 3D printing of pure metals, but they just produce a column. Again, they have not really make additive manufacturing. This one tried to do faster. This is people from Israel. So you see here, they have printed again, but they have not done the necessary steps which are required for additive manufacturing. So the idea is you have a foil, you can print particles from foil in the size of micrometer or 2 micrometer, and then you can go here and sinter these particles or just melt them, and then will be this laser printing and sintering, laser printing and melting. And again, these topics are not yet developed. So it means that you can start to work on this, and this will be successful. So tomorrow, my colleague Michelle Hurst will give here a lecture concerning the gravitational wave, how we measure this. And with her together, we are working on the development of lightweight meta-surface mirrors using these silicon nanospheres, silicon particles, which you can print. So how these mirrors work from particles. You see here the incident light and everything is reflected. And the suppression of the transmitted light happens due to the destructive interference between incident and resonantly scattered light in forward direction. So light from such an array is fully reflected. Where it can be interesting, look, there is a concept, for example, how to make sail. Sail to travel to these exoplanets. We have a lot of exoplanets which are from us quite far away, so 2 light years, 4 light years. And of course, if you would like to make an experiment during your life, so to send something to this exoplanet, then you should to accelerate materials to the, say 10% or the 20% of the speed of light. Then you will, as you see here, you will need probably 20 years to make an experiment. How to do it? You need to have a perfect mirror. So it means when you have, for example, elastic material, you print nanoparticles. I have shown you this is already perfect mirror. Then using light, like it is shown here, you can see this video, you can accelerate this sail and this to the speed of light, and this sail will move to this exoplanet. Just see how it works. The idea. Okay, good. And now the light pressure accelerates it to the speed of light. Okay, you can use also not only laser radiation from the Earth, but you can also use sunlight to do it. But then you can come to the planet, make observation, and the signal will be sent to you back. It will take 2 years for the signal to fly back with the speed of light. But anyway, this is interesting stuff. Okay, since everybody tries to find this life in the universe, and okay, we have now more than 1,000 confirmed exoplanets. These are quite different exoplanets, and for example, my favorite are this one, super-Earth. Super-Earth, they are usually planets which are bigger than Earth, and they have stronger gravity, and therefore, okay, they don't have much mountains, they have a lot of water, and this is like in Bali or with a lot of islands and with a lot of water, very good conditions for life. And this is a super-Earth. You can look into Google and you can learn much more about the properties of the super-Earth. Good, this is one of them, Kepler 186f. Good, now we will go to the different direction. We will go to life. back. So processes of life happen at the nanoscale. So one fertilized egg, you and I and all of us, we started from one fertilized egg, which was then developed, self-organization processes. And you have been born. And everything starts from these stem cells or embryonic-like stem cells. And usually clever people say that life is a journey towards increasing cell specialization. So we increase our cell specialization during the life. And this is how it happens. In 2012, there was given a Nobel Prize in Physiology of Medicine for the guy, Shima Yamanaka, who has introduced revolution in biology. So you can take a skin cell, for example, and you can introduce certain genes, 4 factors, and you can then transfer the skin cells into embryonic-like cells. You can do it with any cells in your body which has a nucleus. What he was doing, he was really studying cells and the genes that are responsible for their pluripotency, and he has found these genes. And now what he can able to do, he can reprogram skin cells, it doesn't matter what, into these induced pluripotent stem cells, and then they can be differentiated in neuronal cells, in cardiomyocytes, it doesn't matter. And these are your own cells with your genetic information, full genetic information. It means taking a single cells of you, we can make an embryonic-like cells again. No good. This is really very important stuff. And one of the topics where we are working, and we're trying to develop technology, laser technology, to print living organs. And we are doing this seriously for a long time already. And of course, when you compare yourself, if something goes wrong, then it is bad. But you can do anything wrong to your car and you can repair it, yeah, no problem. So it means we are here a little bit in disadvantage. So I have a European ERC project, ERC advanced grant in these directions, where we got 2.5 million to really develop technology to print these organs. Just a few words, how many organs we have. We have something like 79 organs, approximately. So if you calculate it in a different way, so we have 206 bones. Baby has more bones, 300, if you don't know. We have 32 teeth. Baby has 20. And counting each bone and 2 separately brings us to the list of 350 organs, which is a lot. Of course, we don't need to make them, since only 5 organs, the brain, heart, liver, at least 1 kidney, and at least 1 lung are absolutely essential for living. So it means we need to learn how to make these 5 organs. Not much. So this is just a simple estimates. You can do it by yourself. Cells in a human body. So just a few numbers, which I don't go into details. And we have also a number of bacteria which are living in our organism. And the total mass of bacteria is not big, it's 200 grams, but they play a very important role. So how we print cells? So we have an absorbing layer here, but we can also work without absorbing layer, it doesn't matter, but for simplicity. So you have here an absorbing layer, laser radiation is absorbed here, and you can generate a shock wave. And here you have a liquid material with the cells, and then this shock wave propels a droplet. You see here how it happens in reality to the opposite side. So advantages of laser printing compared to extrusion printing or to inkjet printing, etc., are as follows. We can print small volumes down to 1 picoliter. We can print material with high and low viscosities. We can print high cell densities, which correspond to the cell density in your living organ. And we have exceptionally high survival, 100% survival rate. And again, everything is simple. So by changing laser pulse energy, you can vary the droplet size, what you can never do using inkjet printing or extrusion. Good. Just I will show you briefly some papers. So what is important with laser, you can print microcapillary network. So this is a capillaries. So we printed here endothelial cells. And the nature is kind enough. So the self-organization processes start here. And so endothelial cells build microcapillaries. So we are the only team in the world which is able to do it now at present. Okay, this to show you that we have printed skin. This one is interesting, since here we printed induced pluripotent stem cells. So we have taken the skin cell, reprogrammed it in the cardiomyocytes, and printed it. And these cardiomyocytes start to tick like your beat, start to beat like your heart is beating. Printing of human-induced pluripotent cells, neuronal stem cells, neurons. So there's also recent publications. So we have studied what are the properties of the brain when we print it. But okay, I will not speak here. You can read about this more. So I will go to the printing of microorganisms. So since we can print small volumes down to 1 picoliter, so you can imagine you have a liquid with microorganism inside. There is certain density of the microorganism. But you can manage such that in the picoliter there will be single microorganism. It means that when you print them, then you print single microorganism from the consortium. Why it is important? Okay, and why the idea works? So the idea really works. So with this woman, she was trying to find this microorganism, which we called in her honor Cpidiforma bonchasmalovskaya. This is a woman. So this is a microorganism living in extreme conditions in the hot spring in Kamchatka, in Chukotka, sorry. And she wasn't able to cultivate this microorganism, to get an access to it, to extract it. But rapidly, with the first experiments, we were able to extract this microorganism and to observe it. So the idea really works. Good. Why it is important? You have heard about dark matter in space, but we have a lot of dark living matter on the Earth. So, you know, for example, the number of microorganisms in the soil, cube size of the 4 times 4 centimeters is equal to the Earth's population. But only 1% of this microorganism can be extracted by standard methods and can be cultivated. So 99% of the microorganisms, we know that they exist, but we don't have an access to them. We cannot work with this microorganism. We cannot cultivate them. Again, the microbial diversity on Earth is very rich, but more than 99% of the potentially 10 to the 11, 10 to the 12 microbial species, we don't know. They remain undiscovered. And 10 to the 30 cells of bacteria and archaea are estimated to inhabit Earth. So this is a big number. So you can read about this. Scale and laws predict global microbial diversity. So we don't have an access to them. And you know that microorganism, I will speak about a little bit later about this. So human microbiota also, for example, what we have here. Microbes colonize wherever the inside of the body meets the outside, eyes, ears, nose, mouth, skin. So we have a lot of microorganisms in our skin, and they change during the day when you go to the shower, etc., and we don't know what they do with your skin. How are they good for your skin or bad for your skin? We don't know this. Also, microbiota, this collective microorganisms which live in us, and I remind you this expression from Hippocrates that all diseases begin in the gut here, and we should take care about our gut, really. We should not eat too much antibiotics. It is correct, but we don't have an access again to this microorganism. So what we are doing, for example, in oral cavity, in human oral microbiome in your mouth, lives 700 species of different bacteria. But you don't know which one, bad one, good one. From this bacteria, 44% are officially named, so only 54% are officially named. 14% are unnamed, but they can be cultivated, and 32% are uncultivated and unknown. Again, and therefore we take a droplet from your mouth, and we print it picoliter like in the microwell plates, and we can culture them. At present, so it is unpublished yet. We struggle with the nature. At present, we have gotten access to all these microorganisms which are in the oral cavity, and we can culture them. And we've given many new names to these microorganisms. And I just show you a beautiful example of this work, where we can stain this oral microorganism, and we can print them using our technology, at this Marilyn Monroe, and this is Andy Warhol picture. So this is a new art, in the sense produced by printing of microorganisms. Good, coming to the brain. 5 minutes, okay, I don't need more. I will go very fast through this brain. So it's interesting to have a brain in laboratory, right? To have a small brain in the laboratory. And this is something what just a few facts about the brain, but probably you know this, it's not so important. This is more important. Gray matter here on the edge of our brain here, this is a gray matter. And the gray matter consists primarily of neuronal cell bodies, or neuronal soma called, from the core, nucleus, and unlaminated axons. And white matter here, white matter consists of bundles of myelinated axon extended out from the soma. And okay, we would like to make a model of this using our scaffolds, for example. And again, you see here how this brain works. This is an artist presentation. Again, you have probably never seen it in your life. So this is gray, and this is white matter, axons, and this is electrical signals, how they propagate inside. So, okay, there are many cells which use or produce this brain. What we have done, this is our scaffolds. This is done also with our company, Laser Nanofab. So, which are commercially available, all this stuff, in the frames of the European project MesaBrain. And we put on these scaffolds neuronal stem cells. Neuronal stem cells, and we have cultivated them. They were, again, induced pluripotent stem cells derived, neuronal stem cell. It means that we take your skin cell and make such a neuronal stem cell here. And then we'll put these neuronal stem cells in the scaffolds and look what happens. So again, this is a paper published here. You can read about this. Good. We see how this differentiation process of this neuronal stem cell starts. So they start to produce primary so-called progenitor cells, and then with this in the culture, they generate first immature neurons. So then later on, they generate adult neurons already. This is a different staining. So they spontaneously do it from the neuronal stem cells and the scaffolds. Then, so appear astrocytes. So this also oligodendrocytes. This is certain cells which are living in our brain, and they are produced automatically during the development. Then also the synaptic connections between these neuronal cells will be generated during the development. And we see these spines and synapses in the electron microscope also here between these cells. What else? In your brain, you have also excitatory and so-called, just a moment, excitatory and inhibitory neurons. So that they keep balance, that you will be not overexcited, for example, if there will be no inhibitory neurons. And the percentage between them is excitatory neurons constitute 22 and 78 to this ratio between them. And the same ratio is generated in our scaffolds. So we generate the same ratio between excitatory neurons and inhibitory neurons in these models. And everything runs, as I said, spontaneously from neuronal stem cells. No good, and okay, so this is a calcium imaging. You see here signals between this. Therefore, it looks like a small brain on a dish, which we have. And okay, this is quite interesting stuff. And this was the last slide which I wanted to show you. So this is neuronal cultures which we developed. And thank you very much for your attention. This is my expert, who is long-term team, who are working with me without PhD students. Okay, thank you very much.
Okay, so thank you for impressive talk, great science, fascinating presenter, and we have time for questions.
Thank you for your talk. So you mentioned that you can basically print the organs, and you...
Yeah, we cannot yet, but we will be able.
Yeah, and you showed that it is possible to recreate even a heartbeat, but what is the limitation that we don't have the artificial organs yet, and that we could implant into humans?
Yeah, of course, it is a complexity of these organs so far, and also, look, everything what happens in you and in me, this is self-organization. So this is the processes which drive self-organizations. And we need to learn how we can use this also self-organization, since we cannot print. When we print cells, this is not yet an organ. So after printing, everything should start to develop, and we should really control it a little bit to give some factors. It is, for example, tricky, since first of all, you need to have blood vessels. You need to have good transport of nutrients to this. It means, okay, and this is a difficulty. You need to have this blood vessel, and after that you can put all other cells, which will be then getting these nutrients and removing waste through this blood vessel. This is a challenge, one of the challenges we are working on. But I think we will be successful during the, some time, 5 years, 6 years.
Thank you.
Okay, some more questions? Please.
So thank you for the talk. And maybe I missed it. So at one time, you're able to print one type of cell. So if you wanted to make an organ, you would have to switch these inks to put different...
No, it is a technical question. So usually we have samples, and we can print different cells during the same time. So we just use parallel, it is simple stuff. So we can print up to 6 different cells simultaneously.
And what about extracellular matrix? Do you put the cells in?
Cellular matrix is a hydrogel, which we are using here. So this is certain sorts of hydrogels which we apply. But usually cellular matrix is done by themselves. So cells, they start to live, and they start to produce this extracellular matrix. And therefore, this happens after the printing. We see that there's some remodeling happens in this media which we printed. And this is an extracellular matrix which is generated.
Okay, thank you.
Good. Probably I can say a few words again why people are doing this, printing, etc. Since, of course, in the future, you will be able, to print, for example, steaks. You don't need to go to grow the pigs, and then you can do it directly, in principle. So there are companies which are already seriously thinking about this. Then you can make leather. You can make goods by printing, for example, skin cells, etc. This is also quite trivial. So many companies, for example, in the US, there is a lot of funding in these directions and then disappear. So there are many possibilities how you can make some speculations in these directions. But what is even more interesting, when you work with microorganisms, and this is technology which I'm like very much. So for example, in microorganisms, you can bring genetic modifications. So you can bring new genes. And you can make your microorganisms so they can produce, for example, milk. So you don't need cow. You can make milk using microorganisms. There are some already companies working on these directions. Of course, using microorganisms, you can generate medicaments. Insulin, for example, is produced long time with the microorganism. So there are many, many, many interesting stuff which where you can use microorganisms and they can work for you. For example, microorganisms, they can generate hydrogen. It means they can generate fuel of the future. Again, that is why printing of microorganisms is very important. And optimization of the processes, what we have with microorganisms, is extremely important. Okay.
Okay, you want it? Please.
Thank you for your presentation. I would like to ask about the mass gained by photons and medium.
Mm-hmm.
So you have mentioned that additional properties or consequences of such phenomena is that we can observe some stretching in cells and
yeah, this is well known. I mean, when the photon enters in the medium, then the medium will be okay, if you assume this Minkowski momentum, then the medium will be stretched. It is very easy. You can just, you know how the light pressure formula look like, etc. You can see it immediately. And you can measure this stretching of this medium, which hasn't been done so far. So the last experiments where people tried to measure momentum of light, they are 100 years old, or even 30 or 40 years old. Nobody was trying to do it again. And it is important, since in dispersive medium, where the refractive index depends on the frequency, you will get new effects. And okay, this is something, okay, read the paper. It's very easy. And then yeah, I have specially it's written so that students will be able to follow. And then you can think about such kind of experiments for fun. Probably you will be able to measure something. It is not easy, of course, since the laser light also produces some heating, also some thermal expansion. It is not really easy, but it can be done.
Okay, I assume I'll just read the paper then. Thank you.
You're welcome.
Okay, one more. If there are no questions from the audience, I would like to ask one. What directions you foresee as from material science, let's say in polymers, for scaffold printing or for maybe...
Yeah, but I know that you are also trying to work on the scaffolds. And Piskarskas, for example, he was saying that Boris, we are successful since we try to repeat your experiments. Yes, we try to do what you are doing, and this is one of the part of our success. He was joking, of course, but anyway, this is... Making scaffolds, for example, when we are making scaffolds, then it is important to look that you will reduce this self-fluorescence of this material. And we have now material scaffolds which have no self-fluorescence, for example. Everything what we do is also commercial, therefore you probably know that we also sell materials for two-photon polymerization. And I can tell you that, which is not yet known, but we have now three-dimensional scaffolds with 3D electrodes, probably, okay. So we can use these electrodes to record neuronal activity and to stimulate neuronal cells. So we are really moving in the directions of brain on chip. Also, I don't know, probably you remember we have tried to make conducting polymers, which can be, okay, two-photon polymerized. Very important stuff also, this started after our work, where we have used upconversion nanoparticles instead of photoinitiators. Then you can use near-infrared light, and you can generate ultraviolet light around these nanoparticles, and then you can produce polymerization through the single photon polymerization. And so I think now 100 papers are directed to this area, where you can use already, okay, just a laser pointer and to make three-dimensional structures. This is also quite an interesting direction, which we are not able to follow on a very fast scale. But I hope you understand what I'm saying about it. Okay.
Yes, okay, thank you. Any more? If there are no more questions for now, so we can thank the speaker for presentation and answers.